having very nicely set the scene in terms of the interpretation of the complexity of the quaternary evolution of the Clyde Basin and the wider surrounding area in Scotland, our next speaker, Katie Whitbread, is also a relatively recent PhD graduate. In Andrew's case, it was the University of Edinburgh. Katie is a PhD graduate at the University of Glasgow. And Katie has spent quite a lot of time modelling high resolution some of the quaternary deposits in Glasgow. So can you tell us something about the pros and cons of deterministic modelling of an urban area? Katie.
Yeah, so after all the exciting environmental stuff, we're coming back down to earth to a certain extent, and looking at the strengths and weaknesses of a particular methodology of modelling that we've used in the Glasgow area. And these models have been developed to try and characterise the superficial deposits that Andrew was just talking about, deposited by a whole range of different processes. And I'm talking on behalf of a whole team of people that have been involved in this for pretty much going on for 10 years, so actually before the CUSP project started. So we're creating these models because we've obviously got complex subsurface deposits. We need to have information about those. We need to characterise them so that we can actually integrate that knowledge in how we manage our environment, how much we know about it. So a lot of that's informed some of Andrew's work about the understanding of the glacial processes that have gone on in the past, but also how we develop applied solutions to problems that affect particularly the urban areas in Glasgow for a range of different reasons. And I'm not going to talk really in technical detail about modelling. I haven't really got long enough to develop that, but I want to try and just highlight that we can model things on a scale that kind of goes from a conceptual idea that geologists generally work from in terms of how we understand our environment and our subsurface environment. We're always building models, and we have always built models generally in our heads. And this is an image of the Geological Survey of Edinburgh, or just Geological Survey in general, in 1914, so that's what we would have looked like 100 years ago. So had a little bit of development since then. Yeah, we had a few more women in it now. So we can develop our conceptual models, which is what we do as geologists all the time. But now, obviously, we can use much more computational processes. We can model the subsurface on the basis of numerical algorithms. And we can do that by putting input data and running stochastic models with an element of randomness associated with them, so that you put in some input data, and for each iteration of your model you might get a slightly different output. Or you can use deterministic mathematical processes, so for every input data you run some kind of model based on physical law, and you get the same output for a given set of input data. So we can do all of these things, and my task today is not to talk in detail about all these different ranges, but to talk about one particular aspect, one particular style of modelling that we've used in the Glasgow area to develop much of our understanding of the 3D structure of the superficial deposits. And this is something that we call deterministic 3D modelling. And what we mean by that is effectively somewhere in between the conceptual and the computational. So we effectively are producing 3D models that have a strong component of the geologist's interpretation embedded within them. And we do that using a software system which has been developed within the BGS, working with a range of people over pretty much the duration with which the CUSP project and before has been running. So we've actually developed our models alongside the software development. And in the process, we basically, the geologist's involvement is to take borehole information, which is usually based on lithology, code it up into some kind of package, set of packages of deposits, and then we can correlate those in cross-sections, produce a whole series of cross-sections to make a fence diagram, and then we have a computational step where we interpolate the packages, the bases and the tops of the sediment units in order to get our 3D model. And that's effectively a deterministic step. So we have this combined process of integrating the geologist's knowledge and the kind of computational side. And so my role today in terms of this talk is to talk about some of the strengths and weaknesses of that, not to compare with other particular methodologies, but to look at the kind of understanding of the processes, how we gained through doing this work in Glasgow. And I'm going to talk, in fairness, I'm going to talk about 3 strengths and 3 weaknesses, but obviously I'll probably spend slightly longer discussing the strengths, which is the way forward. So I'm going to start with the strengths. And one of the main advantages of using this type of modelling is the capability for integrating a whole range of different sources of data. So in Glasgow area, we've got stacks of boreholes. We've got over 40,000 just for the Glasgow area, and the pink outline there is the city boundary of Glasgow, and all of the boreholes these are just the ones that are held in a BGS database. And you can also integrate seismic or other geophysical data into your modelling process. But there's another really important aspect of this kind of process, which allows us as geologists to integrate not just digitally held data, but just something more generic, geological knowledge within the modelling process. And this is what is really fundamental in informing how these models are built. So we can use, particularly in the Glasgow area, the results and the products of extensive mapping that has been done by people over the years, and boreholes that have drilled specific to look at particular deposits. Most of the boreholes that we have are geotechnical boreholes, so they were drilled for particular site investigations, but BGS has in the past gone out to take particular bits of information to help us really build up an understanding of the deposits and how they all fit together. And this modelling process where we integrate the geologist's knowledge allows us a very good way of utilising that in a kind of modelling system. The second one is that it's actually quite a good way of dealing with very complex deposits, and being able to try and map out the complexity. As Andrew's discussed, we've had a complex environmental history in Glasgow, and so we need to try and reflect that and capture that in our models. And in Glasgow, we have basically broken up our package of sediment into 27 main units in the more detailed models that we use. But the advantage of using kind of deterministic method is you can break them up. You can define your package of sediments in any way you like. You could use lithology, you could use some geotechnical property. It depends on what data you have available and what your purpose is. We've used lithostratigraphy, which is a grouping based on a combination of things: the actual lithology of the sediments, the order in which they occur in the sequence, and something to do with the formation process, the environment in which they formed. And this is a list of them with codes, not full names, which is the ones that we use in the modelling. And the power of using a lithostratigraphic model to base our models on is that it actually provides us with some kind of rules by which we can model the characteristics of our deposits and how they relate to each other. This is basically an interpretation of the environments of particular environments of deposition within the Glasgow area and how those units relate. So we have a till on the top line forming under ice, and at the margin of ice we have certain other deposits, glaciofluvial deposits, that form in association with that. And so we can start to pull out their structural relationships, and this can inform our modelling. So we can, based on the constraint of the boreholes, but we can piece that together in terms of how we actually package up the sediment, and that goes to inform how we build up a fairly complicated model. And this is kind of an exploded model, so you can see all the different units, but it actually highlights that buried valley that they were talking about just now, which is the slight pink area at the base there, which gets up to about 80 metres deep in places. So we can start to pull together this package of complex sediments using this methodology, which, as I understand it, is quite difficult to do with purely computational processes at the moment. The final kind of strength, but there's a few slides just to illustrate it, is how we can actually build very versatile and very useful models using this process. We can build them at different scales. So we have catchment scale models where we've used a coarser definition of the stratigraphy, so just 10 units to build the catchment scale model. And that covers obviously quite a large area. We focus in on the Glasgow urbanised area and develop some more high resolution models with a high resolution stratigraphy and also more detail in terms of how they relate, and then look also at building more high resolution models of particular sites for particular applied uses. And these models can be used for a range of things. We've already seen how Andrew has used them to use the catchment scale models to look at the thicknesses of particular units and do analysis on processes. But you can also use the same model by parameterizing it differently to look at things like groundwater processes and flow. So quite versatile in that context. They're also very useful for looking at different applied uses because you can parameterize with different geotechnical properties and build specific high-resolution models that sit within the wider model. And you can also output useful surfaces, so maybe the top of the till or something like rockhead, the base of the superficial deposits. They can have particular uses as well. So there's a lot of different things that you can bring out from the models which can be applied. But to talk about the limitations, the first one to highlight is that it's a very labour-intensive process. We've actually been developing these models since before the CUSP project started, so probably back in 2004, 2005. So I joined the BGS in 2005. So there's been ongoing work since I came to the BGS, although I did leave in the middle to do a PhD. So it's labour-intensive to develop them and takes a lot of man-hours, but and that means that also we've got things that we need to consider as we move forward with the models as to how we integrate new data and how we revise them and make sure that we maintain them in a kind of reasonable, up-to-date format. So that's one of the issues to kind of consider in terms of deterministic modelling. The other is lithological variation, which I'm sure we'll hear more about in the next talk. Effectively, we've modelled stratigraphic units, but lithology is in some ways infinitely complex in geological strata. So there is always going to be an issue to which you need to somehow simplify that. Now we've simplified it to a stratigraphic level, but we can also say that there are variations in lithology within the stratigraphic units we use. So there's a limit to the resolution that we can identify variations in lithology within the context of this process. But what we are developing, and you'll hear a lot more about in the next talk, is ways of looking at using different modelling processes to get into that a little bit more within the context of the deterministic models that we've already built. So how do we actually try and look at lithological variability in a different way using different modelling techniques? So we're also, although it's a limitation of the resolution of this type of model, we can combine it with other processes to actually try and develop our understanding in that area. And the final one is an important limitation or weakness, but we're working on, which is how to quantify uncertainty. How do we know how good our model is at actually representing the ground surface, the subsurface environment? We can talk about it in general terms fairly easily because we know that the kind of accuracy of our model is to a certain extent related to how much data we have. So we can map out where we've got dense boreholes and where we haven't, map out the density of our boreholes. So the top image on that shows the kind of a distribution of borehole density for a particular unit in part of the model area. Red shows areas where there's very few boreholes, so we may have some issues in terms of how accurate our model is, whereas green highlights areas where there's more data and we might be more confident in our model. But geological complexity is also an issue, and this is highlighted by what's going on in the bottom image there. This is pulled apart a bit more by doing a test where we produced a rockhead surface from some model data, from some borehole data, and then we added some more data and produced another rockhead surface, and look at the difference between them. And what we can see from this little kind of sketch plot which I drew is the traffic light symbols on the two bars at the top and the bottom. So borehole density on the top, red areas are where there's few boreholes, green where there's a lot, and orange is a moderate amount. And then on the bottom line, green are areas where it's fairly simple geology, and red is a complex area, which is actually complex in terms of bedrock, so it's a faulted zone. And what this highlights, the two rockhead models, there's one in dark blue and the revised version in the light blue. And you can see that there's areas where they don't match, quite significantly don't match. And some of those are areas where there's few boreholes, but there's also one area directly in the middle, which is an area where there's technically quite a lot of boreholes, but high geological complexity. So we can get a handle on the fact that we have uncertainty and potential errors in some areas related to these two factors. But it's actually hard to be quantitative about it. So when we're using the models for applied uses, we might want to be able to say how likely it is, or the probability of finding a particular lithology in a particular place, or the probability of finding a boundary between units within plus or minus a metre of the place where we've said it would be. So we're having to try and develop statistical ways of looking into that in more detail, and potentially trying to derive some more rigorous assessment of the uncertainty associated with these models, and that's something that's ongoing at the moment. So just to summarise, Deterministic models can be time-consuming to build and maintain. They can be difficult to assess for how predictive we can be about what they tell us about the subsurface, but they're a hugely versatile way of modelling the subsurface. We can apply them at all sorts of different scales for loads of different purposes, and we can derive a range of products from them. And we are deriving, as we'll hear over the next few days, using them in a range of different ways. And they're intrinsically important in helping geologists understand the subsurface more, and also communicate about that to people more. So they're a really great vehicle for us to use to demonstrate aspects of the subsurface and to be able to develop conversations with people so that we can increase knowledge. And that's one of the main ways in which these are being used in the Glasgow area and beyond. So that's me finished.
Thank you very much, Katie. Again, you've beautifully kept to time, so there's a few minutes for questions from the audience, please.
You were talking about borehole density.
Mm-hmm.
Do you have a system to account for borehole quality? We have cases where we have tons of borehole data because they're no good. We also have tons of seismic data, but they're all linked to wrong interpretation of boreholes. So we have high density, but the model is
Yeah. That's an issue in Glasgow as well, because obviously we've got stacks of borehole data in our database, but some of it could be over 100 years old, and some of it's very recent, and varying quality, varying amount of description of what is actually there. It's an issue that we face. I wouldn't necessarily say we had a foolproof method for dealing with it. Within the process of doing the modelling, because it's very strongly effectively geologist engaged in terms of how we develop the models, one of the things we do is actually assess the data as we go, not necessarily in a standardised kind of way, but as a geologist I have boreholes, I download them, I look at the logs, I'm trying to make sense of them in the context of the environment and the other material around it. So we are evaluating the information, I can't think of the word I need to use, but we're evaluating the information as we go along in terms of the modelling process. But I think one of the things that will be interesting to see if we can develop with new ways of looking at data, more big data, more types of data analysis, is see whether we can actually use kind of data mining techniques and other kind of big data techniques to start to find more automated ways of selecting good quality data from data sets. So it's something that we're thinking about and we accept is an issue in our modelling as well.
When constructing a model, we start making a lot of cross-sections,
Mm-hmm.
but these cross-sections obviously do not include all the data points you have in a densely board area, like Glasgow. How do you include the information from the other boreholes that are not cross-sections?
Some of those will go to inform. So we draw the cross sections, but we also draw envelopes. So in plan view. So sometimes we use the distribution of other boreholes to inform us about the actual kind of plan view extents of units in some particular places. We do also take them. We can also take them into account. I will often look at most of the boreholes in my model area before I select which ones to choose. So it's a way of trying to filter and evaluate which are the best ones. I'll try and take my cross-sections through areas where we've got the highest quality. So it might be that what we actually leave out in terms of directly including within the model framework is the poorer quality ones anyway, if that makes sense. There are ways in which you can use those to improve your surface resolution as well. So we could output the surfaces from the models and effectively tweak them with other borehole data in different software packages. So we could actually, if we wanted to do a higher resolution data that includes it, you can include.
Tim. Geoscience 3D now.
Okay.
We can also, this is new development in the software, which can actually include scattered data points. So for where you've got an awful lot of data for a certain thick, you have to export it as a text document and bring those back in and then use those in the control of sections.
So when you do the interpolation step to go from cross section to surface, you can actually include those data points as things that it will interpolate to when it creates the surface. So that's relatively new. So.
You mentioned the time you use the model increases, or I guess increases exponentially the more detail you go. Based on your experience with this regional model, what would be, in your opinion, an appropriate map scale making a model without, well, there are some limits both in time and money, which you can think.
Appropriate map, so equivalent to how you would map and
10,000, 100,000.
I would say that nominally our block models, so for the actual urbanised area of Glasgow, I would say they're probably about 1 to 10,000 scale, which is effectively the most detailed scale of our BGS 2D mapping. So I would say that we would probably build them from that level of scale, and then obviously site-specific ones could be higher resolution. But I would say that our main models of Glasgow are probably 1 to 10. But it depends on the density of your data. If you've got fairly sparse data, you would probably just want to go for a bigger scale anyway. So.
I have a question on the evolution of the terrain in the city. So how to do both normals in the prediction of the...
Yeah. That's a very interesting one actually, because obviously the models hang from a DTM surface, so a digital terrain model. So that's a really core component of the model actually, is how good your DTM is. In urban areas it can be very difficult to get a good digital terrain model surface. And there are often issues with how the borehole start heights relate to that DTM, and sometimes they're real because the ground surface level has changed, and sometimes it's because the resolution of the DTM you have to use isn't sufficient to be able to actually quantify that properly. So that's something we're working on, looking at the uncertainty associated with those boreholes. And there's actually, in other areas of the BGS that do similar modelling, mainly down in England, they have done a lot of work where they've looked at borehole start heights in the context of land use and land use change, to look at what we can learn about made ground and anthropogenic type deposits from exactly those mismatches between, so using the borehole data. So it's an interesting area, that one.
I think we'll have to curtail questions down. I know there are one or two others, but we need to keep moving. Thank you very much indeed.